All right, so hello everyone. Today I'll be walking you through the Climate Change AI Summer School tutorial on estimating coal power plant operation from satellite images with computer vision. This tutorial was originally authored by Andre Ferreira of Transition Zero, and today I'll be walking you through this tutorial. So this tutorial essentially addresses the applications of AI for monitoring, reporting, and verification, in particular for coal power emissions. So by the end of this tutorial, you should have learned about the gaps in emissions data, practical usage of freely available satellite images such as Sentinel-2, and the applications of computer vision models for the purpose of emissions monitoring. So in this tutorial, we'll be introducing two resources. So the first is a data set of coal power plant emissions, including images, metadata, and labels, which you can access using this Google Drive link. And the second is a public GitHub repository with auxiliary code for dataset creation, satellite image preprocessing, and model training, which you can access here in Andre Ferreira's GitHub repository. So we'll start with a quick overview of the data gaps in emissions monitoring. So essentially, the quality and availability of greenhouse gas emissions data can vary greatly in terms of geography as well as how long it's available for. So for instance, the US has what's called the Clean Air Markets Program data, or CAMP-D, where power generation and emissions datasets are made publicly available for each power plant on an hourly basis. You also have similar datasets for Europe as well as Australia. But unfortunately, for most other parts of the world, these kinds of datasets are not always readily available or accessible, or they are self-reported by energy companies, which of course comes with reliability concerns. So to fill this data gap, we look towards global publicly available satellite images like Sentinel-2, collect information about coal power plants across the world. So before we start, let's make sure we have the appropriate settings set up. So in terms of hardware settings, make sure you have your runtime set to a GPU. So you can do this by clicking runtime, change runtime type, and then select the T4 GPU. So that when you connect to your runtime, it should state that you're connected to a T4 GPU. In terms of domain knowledge of the power sector, so you don't need to be an expert in power plants to go through this tutorial. The section below does include further context on coal power plants, but it's enough to know or to be aware that coal power plants have essentially two states. You have one is they're on, or they're generating power, and the second state is they're off, meaning they're idle. And in terms of machine learning knowledge, we do expect some knowledge of Python, PyTorch, and deep learning in general, so that you can experiment with different models or different data approaches. All right, so let's go now to background on coal power plants. So you can think of a coal power plant as essentially having two main operational states. So you have idle or off, and again, generating electricity or on. So within the on state, the power plant can generate different levels of energy, and by extension, they generate greenhouse gas emissions. But for the purpose of this tutorial, we'll only focus on detecting whether a power plant, coal power plant, is on or off. So how do coal power plants work? So as a thermal energy source, coal power plants produce energy by heating up water and using its steam to turn a turbine. In the case of a coal power plant, it burns coal to produce the heat steams up the water. So from an emission standpoint, the main types of infrastructure in a coal power plant that we care about are one, these flue stacks, which are basically narrow and tall chimneys where the waste gases from coal burning, including carbon dioxide, are vented out. So it's basically this. And you have cooling technology, basically what's used to cool down the water that is heated up inside the power plant. So you have basically the cooling towers, which are these wide towers where the water cools down at a pool on the bottom. While big plumes of water vapor come out. And then you also have the water outlet. In the ones through cooling method, the water that is pulled in to spin the turbine and is then pushed straight out of the power plant and back to the river. So in terms of the signals that we're looking for from satellite images, coal power plants can have different signals depending on their operational status and CO2 emissions. So cooling tower plumes generally have very visible, cooling towers have generally very visible signal, which are these plumes, and we'll be focusing mostly on this one. Flue stack plumes can be harder to spot, especially in medium to low resolution images. Flue stack and cooling tower heat, this one is a little harder to detect, even from thermal data from satellite images. It's still too low resolution to really accurately model this. And cooling water flow, this one is hard to decouple from nearby industrial activity. So let's go now to the software requirements of this tutorial. So the main dependency here is a Python library. It was originally developed with version 3.9. It should work at least up to 3.10. So go ahead and check your Python version here. For mine, for example, is 3.10.12. Go ahead as well and install the dependencies and libraries. So this includes the GitHub repository by Andre Ferreira. And then once that's installed, so this can take a couple of minutes, you should be able to import the necessary libraries, as you can see here. If you are using an experiment tracker like AIM, go ahead and run this cell as well. And then for reproducibility purposes, we can set a seed here. We set our seed to 42. All right, so the data in this tutorial uses a combination of the following sources. So we have AWS's Sentinel-2 L2A collection, which are basically satellite images made available both as typical visible light images and as multispectral images with a 10-meter resolution. So again, when we say 10-meter resolution, it means that one side of a pixel is has a distance of 10 meters. Or has a length of 10 meters, sorry. And then it also uses Google's geospatial classification demo, which is a data set of timestamps and coordinates of cooling towers with a label on label indicating whether or not its associated power plant was operating. So go ahead and download this this data set using the gdown function. This should take a couple of minutes, so we'll go ahead and wait while that downloads. All right, so once you finish downloading the dataset, you should be able to get the images from the compressed files. And now we can go on the next step, which is setting up the dataset, as you can see here. So here we set batch size to 64 and the crop size to 64 as well. So let's go ahead and load the CSV of the dataset, as you can see here. So the original author conveniently created a wrapper for instantiating the dataset and essentially preparing the data for model training as well as for model testing, as you can see here. So let's go ahead and run that and explore the training data set, as you can find here. So essentially, it has these following columns. You can see the columns here. What we want to focus on is essentially we have the latitude, longitude, the timestamp, the operations status of the power plant. So this is actually what we want to focus on in terms of the target variable. You also have indicators for the facility ID, the geometry, which is basically the square-shaped geometry centered on the cooling tower, which again is a 64 by 64 pixels in Sentinel-2 images, or 640 by 640 meters, as we previously stated here as our crop size. You have the cloud cover percentage, the cog URL, or the URL for the cloud optimized GeoTIFF, local image path, and the data set indicating whether the data belongs to the training set, the validation set, or the test set. So if you run this cell here, it should indicate how many samples are in your training set versus your validation set, and finally your test set. So the authors do note that the train, validation, and test splits is a spatial split and basically randomly allocating facilities to either the training or the validation sets. Meaning the unique cooling towers can either be in the training or validation set, but not both at the same time. Precautions were also taken to ensure that cooling towers that were very near each other, to the point of appearing in each other's images, would always be in the same set so as to avoid data leakages. So you can check out the get facility set mapper function in the GitHub repo for more information. So we also note that the test set includes all power plants, but only has 2020 data, while the other data sets have data for the years of 2016 to 2017, 2018, 2019, and 2021. All right, so if you run this cell here, you should be able to see a time series of all the cooling towers operation status. You can notice that while some cooling towers have variations in their power generation, most spend the majority of their time generating power, meaning the value for is powered on is 1. Now let's go ahead and run this cell here. And this histogram here reinforces the idea that coal power plants are generating electricity very often. We do see a disparity between positive and negative states. leading to an imbalanced data set, with one class, meaning on, having many more observations than the other class, which is off. Fortunately, there are ways to counteract this, such as applying smaller weights to the on samples in the model's loss function, which makes the model pay relatively more attention to the off samples. And then this next cell here illustrates the cloud cover histogram up to a cloud cover percentage of 50%. We see that most of the images have cloud cover percentages between 0 to 0.5. So hopefully these clouds won't be much of an issue. And then in the cell here, you should be able to find the geographic distribution of the facilities, which you can find are mainly in the US and in Europe. All right, so moving now to the methodology. So the authors, the original author of this tutorial, actually created a simple model from scratch. So they instantiated what they call the small CNN, which consists of 6 convolutional layers with ReLU activation function, 2 max pooling layers interspersed between the convolutional layers, 1 adaptive average pooling layer after the final convolutional layer, and 1 fully connected layer in the end for estimating the final logit, which is essentially the value that is used to estimate if a cooling tower is on or off. So this is what we'll be mainly using during the tutorial, but we do encourage you to try out other models as available on Hugging Face or on PyTorch. But noting that most popular computer vision models were developed with larger images, meaning 256 by 256, as opposed to our current maximum size of 64 by 64 pixels. All right, so if you are aiming to do experiment tracking, you can run the cell here. So AIM or AIM basically is an AI metadata tracker. If you're familiar with weights and biases and MLflow, basically it's very similar. It's used to track your experiments. All right, so for the purpose of this tutorial, it's suggested that you focus on these 2 metrics. So you have the balanced accuracy, which essentially it's the mean of the sensitivity and specificity. So sensitivity, what you may know more commonly as the true positive rate or the recall, essentially measures the proportion of real positives are correctly predicted out of all positive predictions that could be made by the model. And specificity, also known as the true negative rate, measures the proportion of correctly identified negatives over the total negative predictions that could be made by the model. And this balanced accuracy here just gets the average of these 2 values. All right, and then you also have the loss. So for balanced accuracy, our goal here is to maximize it. For the loss, our goal here is to minimize it. So I believe in their original code, they used a binary cross entropy loss. And the goal here is to minimize this value, and we should see this value decrease after each epoch. All right, so you can see now here the code for training the model over the entire data set. So basically, they instantiate the model called small CNN with 3 input channels and 1 output class, which basically takes on 2 values, on or off. So they use a learning rate of 1 e to the negative 3, set their max epochs to 100, with early stopping after a patience of 10. Yeah, so I won't be running this cell because it does take 10 to 15 minutes to run. But after running the cell, you should find um, uh, you should be able to generate a trained model. And using this trained model, which the variable is called the lit model, should be able to run it on the test set, and it should provide you these results. So in my case, the results that I got were 86 869 for the test set balanced accuracy, and a loss of 0.112. You can also run these cells here to visualize the predictions. So if you run the cell here, you should be able to visualize the prediction for a sample index. So here it's set to 0, but you can actually this should be you should have like a drop down here where you can select an index of your choice, and then if you run this code here, you should be able to visualize the corresponding image of for that given prediction. All right, so the authors also tried another set of experiments where they used a smaller crop size. So here they set crop size to 32, and essentially they just executed the same code with just a smaller crop size. But as you can see from the test results, it did not actually improve the model performance. Our balanced accuracy went down from, I believe it was 0.869. Now it's 0.680. So it's actually somewhat worse. And I think in the last set of experiments, the authors used a stricter cloud filter. So here they set the max cloud cover percentage to 5, whereas in the previous runs, I believe it was set to a maximum of 50, if you remember from the data pre-processing steps. The max cloud percentage goes up to 50. Now we want to limit it to just 5%. So running this code, you should get these results. In my case, it did not improve the results actually over. So our best results is still the first run, where we get the balanced accuracy of 0.869. In this case, the balanced accuracy after using a more strict cloud cover percentage is only 0.802. All right, so the results that you're seeing here are based on the original runs by the author. So you might see different values. But from my run, I can also confirm the same sort of conclusions, in that the first model trained with the largest 64 by 64 crop size and the full training set is still the best performing one. So again, in my case, well, the results were I believe 86.9% balanced accuracy. So they state here that while recall can come across as a worse metric, being 70%, it's worth remembering that we're using one individual cooling tower to assess the operation of a power plant. So a power plant can have multiple cooling towers and flue stacks from which plumes come out of. It's often the case that the power plant is operating, but there's only visible plumes in some of its cooling towers. Thus, with our data set of cooling tower images, we're bound to have false negatives of not seeing any activity on a specific cooling tower, while there are while their power plant is actively running. So the authors also state potential reasons for why the models perform better with larger crop sizes. So larger crop size give more context to the model, allowing it to see other infrastructure of the power plant, such as more cooling towers and flue stacks, and being able to see more of the plume if there is one. And with a larger image comes with more features to work on, of course, which is beneficial for the model. And then potential reasons for why it's performing better when being less strict about cloud cover. So a less strict cloud cover allows for more images to be used for the training model. And with a larger data set, there's a tendency for for reaching better model performance. And cloud cover is only estimated using remote sensing methods, and it can sometimes mistake power plant plumes for clouds, and thus discard perfectly capable, perfectly acceptable images. So some limitations of this model. So um, despite having trained a model that's reached an like a decent performance and that has generalized well to the validation and test sets, there's still some limitations to the approach. So one, it's while it's useful to know whether a power plant is operating or not, it doesn't give us specific emissions estimates, which we would need to either work on top of these outputs or change the modeling approach to estimate the CO2 emissions. So feel free to check out the climate trace power sector electricity generation methodology, which the authors have linked here. When relying on visible spectrum imagery from satellites, as we did here, we are hampered by weather factors such as clouds, snow, and bright objects on the ground. This tutorial also only modeled cooling towers of coal power plants, and there are also coal power plants that don't use cooling towers, or at least ones that generate, at least not ones that generate clearly visible plumes. And there are other power plants that aren't fueled by coal at all. So this means that countries with relatively low amount of coal power, such as Brazil, and countries with different types of prevailing cooling technology like Japan, this coal cooling tower modeling approach will be less useful to get country level insights. And of course, the last limitation that the authors have stated here is with regards to the geographic distribution of the data set. So our data was generally all located in the US and Europe, and without really testing on samples from other locations in the world, we don't have we don't really know how well the model generalizes to the rest of the areas in the world. So as a next step, you can try using more Sentinel-2 bands, exploring a time series approach, explore pixel-wise approach, try out different models, including ones pre-trained on Sentinel-2 images, and tackle other types of power plants, such as flue gas desulfurization. So we've included here some exercises that you can try in your spare time. So please do try to try out these exercises. And yeah, we'll see you in our next tutorial.